Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on October 27, 2025, about 2 days ago. It delivers a pixel space generator that unifies normalizing flows and an autoregressive transformer, reaching FID down to 5.67 and IS up to 215.5 with exact likelihoods. The paper is titled Farmer, Flow Autoregressive Transformer over Pixels. And as we will see later, the implications for training and sampling speed are quite significant. In brief, the method splits latent channels into informative and redundant groups, adds resampling guidance, and uses one-step distillation for much faster inference. Figure 1 contrasts three approaches and explains why the proposed design matters. The left panel summarizes pure pixel autoregressive models, which have strong expressivity but struggle because sequences are extremely long. The middle panel depicts a normalizing flow, an invertible mapping that gives exact likelihoods yet samples poorly when forced to a simple Gaussian. The right panel presents the combined method with a dimension split, so modeling becomes easier and sampling remains controllable. Figure 2 shows the full pipeline, which turns image patches into latents and then models their distribution to enable exact likelihood training. The left panel depicts the autoregressive flow, an invertible sequence of steps that maps tokens while keeping a causal order. The middle panel breaks down one flow block that normalizes a token using statistics predicted from previous tokens. The right panel highlights the dimension split, where informative channels are modeled token by token and redundant channels are handled jointly using a Gaussian mixture model. While Figure 3 explains how they speed up inference by replacing a slow sequential reverse path with a one-step student. Distillation here means training a smaller model to mimic a larger teacher so the student learns to do in one pass what the teacher does in many. The left panel illustrates the autoregressive flow reverse process, which reconstructs tokens step by step. The right panel shows the distilled student path that mirrors the teacher forward path, delivering about 22 times faster flow inversion. So Figure 3 described the speedup, and Table 1 lists the two model scales and how capacity is split between the autoregressive transformer and the invertible autoregressive flow. The invertible autoregressive flow is a reversible stack that maps images to latent tokens, which lets training use exact likelihoods. The smaller configuration totals about 1.1 billion parameters. The larger configuration totals about 1.9 billion parameters. Depth and hidden size rise in both the transformer and the flow, so modeling power increases. So, Table 2 compares system performance on ImageNet class condition generation and highlights how the unified design fares against many baselines. The shaded rows show that FID lands near 2, which signals very sharp samples. IS reaches about 250, indicating strong diversity across categories. Compared with JetFormer, FID drops by about 3, a sizable margin. These results also surpass recent normalizing flow methods, so quality improves without complex multi-stage pipelines. So while the last table focused on quality, Table 5 summarizes how the method accelerates inference. The key message is that one-step distillation, which trains the student to mimic the teacher's multi-step reverse in a single pass, slashes the normalizing flow bottleneck. The autoregressive part stays roughly constant at 0.050 seconds. The reverse time for the flow drops from about 0.169 seconds to 0.0076 seconds. Total latency falls from roughly 0.219 seconds to 0.0567 seconds, and sample quality remains essentially unchanged. Alright, two takeaways stand out. Unifying an invertible autoregressive flow with a causal autoregressive transformer delivers exact likelihoods while matching top image quality, and the trio of dimension split, resampling guidance, and one-step distillation makes pixel space generation practical and fast. Bigger picture, tractable likelihoods return to center stage for controllable, scalable generators. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.